Okay, in this example we're going to take a look at maximum power transfer, and this will also provide an opportunity to look at one more circuit that has both independent and dependent sources when we're solving for a Thevenin equivalent. Additionally, this video will correct something that I said wrongly in the previous video about calculating the Thevenin resistance. It is in fact possible to have a negative resistance, and we're going to encounter that with this problem. Okay, so what are our steps when we're doing Thevenin with dependent and independent sources? Okay, we'll identify our load, we'll remove the load, and then calculate open circuit voltage, short circuit current. This will give us our Thevenin, and then we'll use our Thevenin to draw the Norton equivalent, and then we'll solve. Okay? So let's identify the load in the circuit, and I'm going to say that the load in this case is going to be these two resistors, just because it looks to me like that might simplify the circuit to remove both of them. Okay, so I'll redraw the circuit with those removed, and then I'll short the circuit out across the part that I've removed, and now we'll solve for I short circuit. Okay, so forgot this little part right here. This is Vx. So how are we going to approach this? Well, thing that sort of stands right out to me would be to do a KVL equation around this loop here. Okay, and because we have a current source here, we'll actually have to use the idea of a super mesh and cross over here. And then that will also give us an auxiliary equation. So let's label our mesh currents, and I'll call this one I1, and I'm just going to call this one ISC. Okay, and according to this I1, this is our polarity on that resistor. Okay, so let's do KVL then at the super mesh, and I'll start down here and work my way around. So the first thing we do is we go through the positive terminal of the 4 ohm resistor, and that's times I1. And then we go through the negative of 4 Vx. And here we go through positive Vx. And that's it. That takes us back around to 0. So to simplify this, we have 4I minus 3 Vx equals 0. Now remember, whenever we have a super mesh, there's always going to be an auxiliary equation that falls out. And in fact, in this particular circuit, because we have a dependent source, there'll be 2 auxiliary equations. Let's take a look at them. I'm actually going to write it up here just so I don't run out of room down below. The auxiliary equation 1 is going to be the branch that we've crossed over here. And so we can see that ISC minus I1 equals 2. So ISC minus I1 equals 2. And we're going to rewrite this as I1 equals ISC minus 2. Okay, and then the other auxiliary equation that we have is right here. We have another way of speaking of I1, right? It's Vx over 2. So I1 equals Vx over 2. Or Vx equals 2I1. Okay, so we can use these interchangeably. Okay, so now what we'll do is we'll use this idea to simplify the equation. So first what I'll do is I will replace Vx with I1. This is going to give me a single equation with a single unknown. However, well, we'll see what happens with that. Okay, so where I see a Vx, I'll put in 2I1. So we get 4I1 minus 3 times 2I1 equals 0. And then this gives us minus 2I1 equals 0. Okay, we can't really do a heck of a lot with that. However, we can plug this equation in. So we plug this one in here, and now we'll plug this one in here. And this is going to expand it and allow us to solve for I short circuit. Okay, so minus 2 times I short circuit minus 2 equals 0. This is minus 2 ISC equals minus, see, this is positive 4, and then move it over to the other side, negative 4. And so ISC then is equal to 2 amps. Alright, now let's look at the open circuit voltage. Okay, so this is the drawing that we have for that. So to calculate the open circuit voltage, and again, I guess I forgot this part of the circuit. Vx. To calculate the open circuit voltage, let's do a KVL equation around the outside and see what that gives us. The reason for doing that is that it's going to allow us to equate VOC to something, okay, to the outer loop. So again, I'll start down here, and this particular polarity is telling us what we're assuming the current is. So just to maintain continuity here, I'll use the same polarity. Okay, so we'll start down here and we'll work our way around. So we get plus 4 times we get plus 4 times I2 times the current. Now notice that there's no current flowing through here. All of the current's flowing through here. And this current source is telling us that our current is flowing in the opposite direction of our polarities. So that's going to be negative 2. Okay. And then continuing on, we go through the negative terminal. So minus 4Vx. And then plus Vx. And then finally plus VOC equals 0. So then this is minus 8 minus 3Vx plus VOC equals 0. We can now calculate Vx, and then we're basically done with this. So we can calculate Vx by knowing that the current flowing through here is 2 amps, and we have the resistance. Again, we have to consider the idea that this Vx is not following the passive sign convention. So what I could say is that negative Vx is equal to 2 times 2, or 4. And so therefore Vx equals negative 4. Okay. Now we'll take this idea and plug it into this equation. And what we get is minus 8 plus 12 Vx, plus 12 plus VOC. Okay, and so then that equals 0. And so VOC then is minus 4 volts. Okay, so there you go. There's a situation in which we have a negative resistance. Look at this. We have positive current, negative voltage. So when we go and calculate our R Thevenin value, R Thevenin equals VOC over ISC, and that's minus 4 over 2, which equals minus 2 ohms. So now let's draw that in to the circuit and see what we get. So VOC here, negative 4 volts, so I'll just flip the polarity. And remember, when we drew our circuit, we pulled out 2 resistors. So we got to put those 2 resistors back in now. Okay, so here's the one, and so it looks like that. And this is minus 2, and this is 4. And this is the resistor that we're trying to figure out. What resistor do we want to put in there to get a maximum power transfer? Okay, and this is minus 4. Okay, so remember our diagram before. We need this to equal the resistance up here. So RL simply equals 2 ohms. Okay, and if you want to read a little bit more about negative resistors, there is an article in on Wikipedia that you can read that has a little bit of information about the characteristics of those resistors. So good luck with it.